In this video, we're going to discuss how you should actually go about interpreting the derivative and what it tells you about a particular problem. But first, we're going to discuss some notation, and this notation is just going to help us understand what's happening within the problems. So let's first talk about the notation that we already have, and that is if we call a function f of x, then we've been calling its derivative f prime of x. This is called the Newton notation, and you could actually use it too for y. If we said y equals some function, the derivative would be y prime. But we're going to add a new notation. It's going to really help us understand what's happening with the units of a particular function. This notation is called the Leibniz notation. And so let's say we had the function f of x again. What we do is we think of the derivative as actually being some operation. And so he would say you would do d dx. Take the derivative with respect to x of f of x. Or he would call that df dx. And we're going to talk in a minute why that notation is helpful for units. And so likewise, if we had y, then Leibniz notation would say we would do d dx of y, or we would call that dy dx. So let's look at how we're going to use this notation to help us. So for example, we're going to write Leibniz notation of the derivative and give the units for the following situation. The distance from the ground d in feet of a skydiver is a function of time t seconds since the diver jumped out of the plane. So the way we've formerly been used to this, we would say d is a function of t, right? Where we would plug in some time and we would say the distance from the ground. So using the Leibniz notation, we would say that's d dt of this function uppercase d lowercase t. And so that would equal this. Lowercase d of uppercase d dt. So that would be our Leibniz notation. But now we want to talk about the units. Well, hopefully you notice you have your distance on the top and the time on the bottom. And distance is in feet. And time is in seconds. So we would say the Leibniz notation is d uppercase d dt with units feet per second. Okay, so we're going to move on with some interpretations and really understanding notation, but a few things to remember. The derivative tells us the rate of change at exactly one input value of the function, at an exact point within that function. A rate of change tells you the amount of change you expect in the output when you increase the input by 1. When a function is increasing, the first derivative must be positive, and when a function is decreasing, the first derivative is negative. So do we think the derivative from our skydiver example would be positive or negative? I would say it would have to be negative. And the reason is the distance was what the function is. The distance between the skydiver and the ground would be decreasing, so therefore that function would be a negative, or it would have a negative derivative. Okay, so just some notation things again. If we define our function as f of x and it equals some value, then this x is really our input, and the value f of that input is really our output. It's the value of the function for that input. Our derivative, hopefully you recall, it changes with time, or it changes as we put different input values in. So here, x is still an input. But this value is the rate of change at the input. So this notation on the right, f prime of x, is telling us something totally different than what f of x is telling us. So here we're going to look at how we interpret that notation. The temperature in degrees Fahrenheit of a cold yam placed in a hot oven is given by y of t. So y of t is telling us the temperature, where t is the time in minutes since the yam was placed in the oven. Would y prime of t have a positive or negative value, and how do you know? So y prime of t is the first derivative of y of t. I would say that that has to be positive. And I know this because the temperature of the yam is increasing. When our function is increasing, the derivative must be positive. What are the units of y prime of t? Well, again, we're going to think about the Leibniz notation. So d of y of t over dt would be dy over dt. And we know dy is temperature and t is time. And if we're talking about the temperature here, we're looking at degrees Fahrenheit, and our time is in minutes. So the units would be degrees Fahrenheit per minute. Explain the practical meaning of y of 15 equals 155. So here, 15 is the input, and 155 is the output. And we're just talking about the original function. So if 15 is the input, and input is time, 155 is the output, and output is temperature, I would say this statement is telling us at 15 minutes, the temperature of the yam is 155 degrees Fahrenheit. That is something totally different than this next statement. Explain the practical terms of y prime of 15 equals 3. Well, again here, 15 is the input. But 3 is the rate of change at 15 minutes. The rate of change, remember, we're going to express that with this up here. That is going to be represented with this. Y prime of t is in degrees Fahrenheit per minute. So I would say this statement is telling us at 15 minutes, the temperature of the yam is increasing 3 degrees Fahrenheit per minute. That means that we would expect each additional minute after 15 minutes to produce a 3-degree Fahrenheit increase. And you might be thinking, well, how did I know this was increasing? Since 3 is a positive number, when the derivative is positive, we know the function is increasing. So if we wanted to estimate y of 17, that's 2 additional minutes from 15. And we know at 15, the temperature is 155 degrees. Plus, the temperature is increasing from 15 minutes. Well, if we're getting a temperature increase of 3 degrees Fahrenheit per each minute, we've got 2 additional minutes here. So I would say we're going to add 2 times 3 to the temperature at 15 minutes. And I would estimate y of 17 will be 161. And so what that is telling us is at 17 minutes, we expect the temperature to be 161 degrees Fahrenheit.